Hello everyone, and hello everybody online. Yeah, I see more people online than in person, but that's okay. I think it's my great honor to invite Dr. Lin to give us a talk. And I just have a very brief introduction about Dr. Lin. Um, Dr. Xuemei Lin is a lecturer in civil engineering at the University of Dundee, and she obtained her PhD degree from the Hong Kong Polytechnic University, and he's now a member of the Institute of the Materials, Minerals, and Mining.
Yes, please go ahead.
And her research is mainly focused on sustainable infrastructure and also high-performance steel structures. And today, he will be giving us a talk, which is mainly focused on her research over the past years, focusing on the structural performance of the bolted connections made of high performance steels. Yeah. So I think that I can leave the stage to Dr. Lin. Let's welcome.
Good afternoon, everyone. Thanks for coming for this talk. Thanks for Dr. Yun's invitation. So today I will mainly talk about the structural performance of bolted connection made from high performance steel. Actually, I will mainly cover the high strength steel, what I was mainly do and establish the analysis framework, something, and extend a little bit to the stainless steel. So that's why I call it high performance steel. And this talk, I will mainly cover the following content. This one, okay. Out.
It's because
No
I
mouse.
need to minimize this.
Oh. Oh, yes, this one. Okay, thank you. So today, my talk will be mainly cover the following content. I will beginning with a brief introduction of the high-strength steel bolted connection, and then will followed by the main research findings and discussion. Then the last will be introduce a little bit how to transfer the methodology established based on the high-strength steel to the stainless steel bolted connection. So first is the high-strength steel. This kind of steel material is a normal yield strength larger than 460 megapascal. So this material has a high strength to weight ratio. If using this kind of material to make the high strength steel member, that kind of member usually will have reduced section size, and the self-weight usually will be relatively lower compared with the mild steel. So if we further use this kind of high strength steel member to make the structure, okay, and those kind of structure will use, you can achieve the longer span and larger column free span space compared with those made by the mild steel. Then it means if you apply the high strength steel to the civil engineering structure, so we can achieve the considerable economic benefits and the sustainable construction. And then how to realize this kind of application? It means you need to have the efficient connector way to put the high strength steel member to be together and then to have the structure. It means the effective design of the connection is very important. Actually, the connection way has the bolted and welded. So I want to minimize this one, cannot, right? It covers something. So the effective way connection have bolted and welded. Today we will mainly cover the bolted one. So let's see the current design method for the bolted connection. And for the bolted connection, let's see here. Okay, here. So the current design rule of the bolted connection from Eurocode actually is mainly based on the test data from mild steel bolted connection. But as shown here, you can see the strain stress curve from the test. Compare high strain steel with the mild steel. You will see, of course, the yield strength or tensile strength is larger. However, the strength rate, tensile strength to the yield strength ratio and the ultimate strain is relatively lower. It means the ductility of the high strength steel is relatively lower compared with the mild steel. And this kind of effect will affect the structural behavior and the tensile strength of high strength steel bolted connection under tension. So it means whether this current design rule of the bolted connection still suitable for the design of the high strength steel bolt connection. So we don't know. That's why we conduct some investigation about that. And let's see further about the current design equations for the bolted connection. For the bolted connection, they can be failed in different kind of failure mode. So the first one is just a fracture across the critical section. If like this kind of connection, the design equation will be used the net section resistant design equation. It is very simple, just the net section area multiply the tensile strength level and multiply a factor to over the safety factor. This is from the Eurocode. And then another, what if the bolt, we just arrange a little bit stagger. So this is a kind of normal way, want to arrange like this to make better use of the tensile section area. It can make the tensile resistance of this kind of bolt connection be larger. So this is a very typical way to use. However, we have mentioned, compare with mild steel and high strength steel, the ductility is relatively lower. So whether when this under tension, the stress development across the critical section, no matter without stagger or stagger, whether along this critical path, the stress can still develop fully up to the ultimate level. Actually, we don't know. It will be affected whether this kind of current design equation still can be applied for high strength steel. Actually, recent years, the Eurocode have updated from the mild steel to BS 700 grade already, and to make the equation a little bit modified already, but still have not included S960. And before, when I do the study, actually this new version has not come out. So this is one typical fracture, just across the net section. And then another typical way is like the block of the material be tear out. So this is called block shear strength. And the current design philosophy in different design rules, it will just consider that this kind of block, the resistance is consisted of the tension in the section here. Okay, just the net section here. And another part is from the two sides of this shear. So they are just combined together and then we'll get the resist from this, the whole block material. So that will be called block shear strength. So we can find that for this net section area resistance, we all think about, okay, the net section area multiply FU. It's okay, down. But for the shear plane, different design code have the different specification. For example, Eurocode, it will previously, they consider, we just use yield strength, not consider its health strength hardening and developer up to the tensile level, just to FY yield state. And currently they have modified. They have upgraded to 2024 version and to consider both. But both is like here. For the gloss is just along this line to be considered the shear plane area. The blue line is just across the center of the hole. It will call the net shear plane area. So either based on gloss, either based on the net. So they have different regulation. For the North American, the code also consider this both too. For the net, they will consider to the ultimate, to the gloss, they just consider, okay, just at the yield level. And for the Canada, they have the modified, okay, so actually the strength is between, it's yield and tensile between. They just, okay, simplified, take the average. So we can find that actually the different design codes have different design specifications. They are not consistent. Is there any way to find out a uniform design formula to just regulate the block shear strength? So this is our another main objective. And also the current design data is mainly lower than the 700, so not up to the S960. We also want to extend the database. So then our mainly study is with the following objective: want to address the above research gaps. So to investigate the structural behavior of the high strength bolted connection first, covering S690 and S960. Then to examine the effect of geometry, configuration, stagger, non-stagger, and the bolt space something, and also the ductility and the strength ratio of high strength material to the resistance of the high strength steel bolted connection. Following that, to evaluate the applicability of current design rule to the high strength steel bolted connection, including the above two typical failure mode, net section fracture and block shear. At last is to propose the design recommendation accordingly to the different typical way. So for the first part is mainly to use experimental and numerical combined together methodology. And for the staggered, how to calculate the net section, actually the design rule have provide the calculation way. It's called S squared per 4G rule. So this is the typical calculation method, the North American code, the Australia, the Eurocode, always like using this rule. But we will re-examine whether this rule still can apply to the high strength steel. So then let's see the first. This is a test program. We have finished all the testing using the universal tensor machine instrument, and a total of 105 specimens were tested. And the steel grade covers these two high strengths, and also conducted the mild steel wanted to do the comparison, and the tester parameter to have account for the bolt spacing, both perpendicular to the loading direction, also the parallel to the loading direction, and also age distance and the number of the bolt row and bolt pattern, stagger, non-stagger. And so this shows a typical failure mode from the tested specimen. You can see the above is just the net section happened across the critical net section here. It's the first row, and the lower the line shows the block shear. You can see the block of the material, the whole block just pull out. And we just divide the test program into three phases. Here is the non-staggered failed by the nut section. Here is the staggered and failed by the nut section. And the last phase is block shear. So that's why I split here, have different number. I just do different in phase. I will introduce the results and analysis, something just according phase by phase later. So this is a test program, and then is numerical. Following the test data, we will develop the numerical model to do the further analysis and the parametric study. So this is just based on the abacus to develop based on the measured dimension. And then is here setting the boundary condition. This is to simulate the testing program. One end is fixed. Another end is just applied by the displacement load, like the machine grade. And then for the contact property, this is a universal way, typical way to setting. And how about the material model? For the material model, filled by the a nut section fracture. This is simple. We just use the fracture model of the GC fracture model and to do the calibration. Only 3 parameters need to calibrate it. So this is very easy. We just compared one by one, validate it. But for the block shear, it will be a little bit complicated because the whole block tear out. Not only tensile will also have shear, so they will combine together. We want to account for the effect from the stress, triaxiality, and the large angle. So the GC model cannot satisfy anymore. So we extend the fracture model just based on the BW they proposed that one. And then we need to calibrate 4 parameters based on our old test data. So this is a typical fracture we have calibrated after the final. We got the triaxial, the fracture strength and the large angle, the 3 parameters. We plot the curve. Then let's go to the results, analysis results. I will introduce phase by phase, and each phase will cross the experimental results and the numerical results, and then is design method evaluation. So let's see the phase 1 first. So phase 1 is nut section fracture. This is a typical testing curves of the road displacement. I extract 2 groups of each is 3 to compare. And here, this is a test to predict ratio. So what does this mean? Let's see later here. I explain this one first. So this is displacement at the ultimate state. I extract the displacement for each specimen to do the comparison. Let's see here, the green one is mild steel and the other is a high strength steel. You can find that the mild steel displacement is larger, right? So this can be indicate that the ductility of the bolted connection made by the mild steel is relatively larger than the high strength steel. This makes sense, right? Compared with the material property, we can instance that. And how about the test ratio? So let's see here. I just cross one line across the 1 unit here. So this value is tested ultimate load over the predicted resistance, ANFU. If this value is larger than 1, it means the cross nut section's strength can be developed, fully developed to the FU. It means the nut section resistance can be achieved by the design mode, ANFU. So if it's lower, for example, it means the stress across the critical nut section cannot fully develop. So that is the philosophy. And for here, nut section without stack, everyone is about 1. So it means can be fully developed. So just look at the test results, we can find, okay, mild steel, high strength steel still can be used it. Just go for that equation. So that will be too simple. We will to look at further to based on the numerical study to think about why the high strength steel ductility is lower, but still can achieve. We will think lower cannot fully, right? But why it still can fully. So this is the first we found based on the numerical. We just plot the stress development distribution across the critical nut section. We can find that the dotted line is the FU level of the each material. And we can find that for the stress distribution at the ultimate state is already fully developed. Even the mild steel is much higher than the FU already. So for the high strength steel is above, and then minor error is lower, but average is above already. So that's why we can achieve the ANFU. And another effect is about here, why they can develop so higher. When we look at further to be the stress distribution across the critical nut section, very detailed, we will find that at the stage of the nearly ultimate state, we found that actually under tension, the critical section's stress distribution is not pure tensile stress. It's the biaxial stress. It's half the tensile is also have a little bit of the tensile is here. So that's why. This is because the hole is here. When you under tension, you want to make the tensile plate to have some necking here, right? It wants to have the deformation, but the hole, it also will restrain, will want to stop the concentration here. So that's why it will induce a little bit of tension here. So that's why biaxial stress actually have mentioned in 1980 by someone, but then, and no one mentioned that. Actually, this is biaxial stress. We can analyze it by the Morse circle stress. We found that if under biaxial stress, both is tension, not tension, compression, both tension, it will have a kind of reinforcement effect there. So that's why, based on these two behind reason, and then we can explain why the lower ductility of hydrogen still can have the ANFU fully development. Okay, this is the phase 1. And then is for the phase 2. Phase 2, we also just do, because we wanted to make the analysis consistent, also compare the ductility first. So this is no doubt high strength steel is lower than the mild steel. And then when we compare the test to predict ratio, we will find that if you plot the one line is here, you will find that S squared 960, there are some is lower, right? So that's why we also need to analyze. So for the staggered, actually we have a total 33 hydrogen steel, and then 22 is nearly can reach, but 11 hydrogen steel is a little bit lower, but nearly to the 1 is already. But I still want to look at further why that will happen. So let's see. We also plot the stress state at different pattern. Let's see here. The first one is the S over G is equals to half. So what is S? What is G? S is the distance of this two borehole along this loading direction. G is the gauge space perpendicular to the loading. So this way is S, and this way is G. This is S over G. And then let's see, it's lower than 1. The stress state is biaxial, it's tension, tension. However, when you look at further, if the S is stacked larger, so like this, we found that it's no way biaxial tensile stress, it becomes tensile compression. And when you analyze it by the Morse circle, you will find that if one is tensile, one is compression, it will make the resistance lower. It will it will be not the reinforcement and will be weaker a little bit. And for the here, if we double the pattern, have the different, have this way, similar like the symmetric, it will enhance the reinforcement. So this is, we just based on the validated numerical to find out the behind reason why the staggered will have different, why the symmetric pattern will have a larger ratio compared with the non-symmetric way. And then another is, you remember we mentioned the S squared per 4G rule, right? So for this staggered, when we calculate the area of the staggered section, need to use the S squared per 4G rule. And this rule is based on the assumption that, okay, the fracture path just goes through the center by the center borehole. We want to look at further whether the development of the fracture path is actually follow this kind of path. We just loading, unloading to open the cover plate to check and how the developer of the fracture path. We found that combined with the test and the numerical to look further, we found So actually the fracture is not just occurred on the linking line. It's a little bit other way. So it means the theoretical calculation of the S² per 4G rules assumption maybe need to revisit. So what we do is start from the theoretical background first. This calculation is the basic theoretical formula how to calculate. For example, this is a staggered net section. Usual way is the gross section area to minus this one borehole and then partial of the borehole, just using x DO. So the x is between 0 and 1. But how to determine the x value? So based on the maximum principle, stress principle, previously they give a calculation equation like this. And then in 1920, Cochrane just simplified this one to here. And then the current S² per 4G rule actually based on this to do the further simplify to remove the 2D. And when we look at the background, just to compare these two equations first, to compare whether the determined x value is the same, we compared like here, when the G/DO is lower than 3, we found that the blue line is from the equation 1, is exactly x value by the complicated one, and the green one is from the Cochrane's equation. We found that blue is always lower than the green. It means the x value based on the equation 1 actually was overestimated by the green one, right? So we needed to do the calibrated a little bit. That's why we propose a factor for kg to account for the effect from the G/DO effect to the calculation x. So then this dotted line, the red, is after calibration, and we calculate the x value. You can find that this one is consistent very well with the results from the originally complicated one. But why, when we do the test data, we found that, okay, the predicted value based on S² over 4G rule still seems like a good prediction. What's the reason? The x value have overestimated already, and why the result is still okay? So behind the reason is here. Actually, the S² per 4G rule, they just ignore this TOD is here. If you remove this one, it means the x value actually you are underestimated already. This is over and then cancel out. So that's why the current S² per 4G rule still can provide good prediction. But the behind the reason, no one have mentioned before, and we look at further to find out that one. So then is based on phase 1 and 2, we conduct the design method evaluation. So we mainly to conduct the reliability analysis for the net section resistance, staggered or non-staggered, followed by the Eurocode EN 1990. So then here we will find that the calculated partial factor is always lower than the 1.25. And 1.25 is the suggested value from the design code. So it means it's conservative. We can use the current one. It's okay, just to use that 1.25. And then it's go to phase 3, Brock-shear failure. So for the Brock-shear failure, this is a normal way compare ductility. And then the key part is we have mentioned the design code provide inconsistent design equation, right? So we just based on the test data to compare the predicted and the tested value. We found that the first one is Eurocode and followed by the American code. This is Canada. The Eurocode is conservative. Each ratio is here is above. And for the American code is conservative still, but for the Canada one is unconservative. The main reason is from the definition of the shear plane resistance. So is there possible to find out a universal one, and then to need to further investigate failure mechanism first, based on the mechanism, and then to check the design philosophy, right? So let's see the failure mechanism. Let's see the shear plane resistance. It consists from the area from the strength, right? First, let's see the location of the fracture plane on the shear. So this is a loading, unloading a progress. We just extract the typical one, and then to plot the stress development state at each state. Let's see. I plot like this here. So this curve is the shear strength, and is the equivalent plastic strength, not the shear stress, because we wanted to see the fracture path, how to develop, and then to see the deformation where is the most concentrated. So if we link it together, we will see it's always between. Actually, it's not just in the middle, it's the between. So then the location we have defined is the between. And how about the value of the shear stress? It's Fy, it's Fu. So we don't know. This is the 3 just with the 2 rows of the ball. We found that at the ultimate state, it seems like can be fully development. And if look at further from the 2 ball row extend to the 4 ball row, we will find that nearly the end, actually the shear cannot redistribute fully, right, at the ultimate state. It means you cannot just consider it's 0.6 Fu already, or just ignore the strain hardening just to think about its 0.6 Fy already. So need further investigation. It actually depends on the material property and geometry configuration. It's longer, the redistribution will be difficult. So will be different. And mild steel compared with high strength steel, ductility is higher and the redistribution will be easier. So how to qualify this kind of effect? We do like this. First is based on the proposed equation from other researcher. So Lipter from Australia, they proposed an equation for the cold reduced steel sheet connection. They mentioned that actually just using the shear plane like the average of the net and gross, and then then for the shear strength, just use 0.6 Fy. They just exclude the strain hardening. This is the best cold reduced steel. And they actually propose another. And for the hot rolled steel, they think about, okay, the strain hardening actually fully developed. And then we can consider just use 0.6 Fu. This is the 2 equation from their paper. So let's see, based on our test data, whether these 2 design equation can be used. So for the hot roll, we will ignore the shear lag effect. So we'll be simplified like this, these 2. This is for the mild steel fully, and this is for the high strength steel, ignore the strain hardening. So let's see this one and this one, whether it's suitable for us. Based on our test data, we found that, okay, predict very well. So that's done. No. So the test data is not so large. We need to extend a little bit. So we extract the test data from literature, including mild steel, high strength steel. It's around 147. We do comparison again. We found that the paper one is a mild steel. It's okay. And then the average of the test to predict ratio is 1. So this seems okay. Mild steel considers a fully strain hardening, fully developed. And for the high strength steel, you will find that a little bit above. It means the high strength steel is underestimated just by using the 0.6 Fy. So maybe there are some reasons we can look at further. I compared many parameters to the ratio until I found that when I plot the test to predict ratio versus the FU over FY ratio, the strength ratio, we found that this above dot of the Hessian steel actually is exactly this above 1. And when we look at further the strength ratio, it is ranging from the 0.12 to 0.28. It means if the strength ratio located in this range, they actually have some string hardening already, but we ignored. So that's why we have the underestimated results. And then how to account for this factor from the strength ratio. So this is another work we done. We want to introduce a factor to account for this kind of effect from strength ratio. But how to qualify this factor with from our test data to fitting expression for this Km directly. And then let's see, if do like this, our design equation will be expanded to the step function. The up boundary and the lower boundary, you can see is the same with the Lipton's equation for the high strength steel and mild steel. And we also have the middle to consider the partial string hardening from the high strength steel if the ratio is between 1.8 and 1.35. So this is our work in the middle. We want to have the universal design equation to cover the mild steel, high strength steel block shear failure. Then this is the developer of the of the value of the factor, and then need to validation, right? So validation we based on the 147 data from literature to do the independent validation. So we can find that very well. Mild steel, high strength steel, both they can provide a very good prediction. So this is our equation. And then last is to do the design recommendation. For the block shear failure, this design equation, we do the reliability analysis according to the North American procedure, not for the Eurocode. Because Eurocode is just one partial factor for one item. We need to introduce 2. So for the North American, we just consider 1 is okay. So here we follow this one, and just based on to check whether the suggested resistance factor phi value of the 0.75 still can be combined or used for this proposed equation. And the results show that our beta is 4.7, a little bit larger than the suggested one. So it means conservative still can be used. So 5.75 can be used combined with the proposed equation. So this is phase 3. Then we can go to the main conclusion for the high strength steel bolted connection already. So for the bolted connection, the ductility behavior, we compared with the displacement at ultimate state. So a lower ductility exhibits the relatively lower ductility and lower the test to predict ratio. It's in general. And for the high strength steel connection, why they still can achieve the net section resistance, although the ductility is lower, we found these 2 behind factor. One is efficient stress redistribution, another is the biaxial stress effect. Then it's go to the S²/40 rules, the vertical background. We revisit and then propose a modification factor to account for the effect from the G over DO. And then is for the block shear strength, we modify the design equation and then to have the consistent one. The last is to do the reliability to check the partial factor or safety factor still can be used for the high strength steel. So based on the bolted connection of the high strength steel, we just follow the similar like the standard procedure, test, numerical, and then have theoretical, and then is combined with reliability. And we think about whether this kind of investigation or study can be extended to another high performance steel material. So recent years, this is funding based on the high-strength steel. Our center in Hong Kong Polytechnic University before, when I do the PhD and postdoc, they published a report and then include our research results, and that is a kind of technical report to support the new version of the design code. So we think about whether we can extend our methodology to different kind of high performance steel. So we think about the stainless steel, duplex or the austenitic. They have different material property, especially the austenitic one. They have the significant strain hardening. So strain hardening, we have mentioned that for the shear plane, strain hardening is very important to develop the shear stress level, right? So for the duplex, it is similar like the high-strength steel, but the ductility is higher, much higher. It will also affect the structure behavior of the bolted connection made by the stainless steel. They will be different. So we follow in the similar investigation way, found that for the duplex one, actually the ductility, of course, will be larger. And then important is the block shear failure mechanism. We want to check whether steel can use a philosophy developed based on the high-strength steel. For the duplex one, we found that the similar failure mode is similar. So the philosophy is okay, but the design equation we have modified already based on the stainless steel's material property. However, when we transfer to the austenitic, we found that, okay, seems different. For the austenitic, actually the strain hardening is very significant when the net section's strength develop and hardening, then the shear plane actually have much time to develop their shear strength. Then the interesting finding is that for the austenitic stainless steel bolted connection, the fracture first occur along the shear plane, not the net section area. So this is a very interesting finding. Then it means the design equation for the austenitic stainless steel bolted connection, we need to totally refine. So this is our another work recently have published already. We also propose a different equation based on we observed the failure mechanism. Then is go to the future. So the current analysis framework can do high-strength steel, can do stainless steel. And the recent years, the 3D printed steel material is very hot topic. And then this kind of materials and material property even more complicated and will be no longer isotropic, will be not isotropic. So the failure mode of the body connection will be even more complicated. So we need to re-investigate it. And aside is, how about if the loading condition is from the room temperature, we go to the high temperature. So will be another complicated one, and combined together will be more complicated. So this is the future work, and we will do together with Dr. Xuemei. Yeah, so if you are interested, so they are the reference. And thanks all. Thanks, Dr. Xuemei's invitation. Yeah.